In this video, I'm going to give some demonstrations of how to solve equations using the natural logarithm and the natural exponential function. So for this, we'll be doing a combination of taking apart and putting together to solve equations. Here's our first example. So we're going to solve 5 to the power x equals 20. Okay, I encourage you to take a moment, try to figure this out, and then I'll demonstrate the solution. Okay, first, just some thinking out loud. What is 5 to the 1? 5 to the 1 is 5. What about 5 to the 2? 25. And then 5 to the 3 is 125. So 20 is right in there, which means that we ought to be able to find a number somewhere between 1 and 2 such that 5 to that number equals 20. It's probably going to be closer to 2 because 20 is closer to 25 than it is to 5. But now how exactly are we going to do this? Well, here's where logarithms come into play. What's different about this equation compared to other equations that we've solved in this course, the unknown is up in an exponent. And the big important thing you can do with logarithms is pull things out of an exponent. So let me show you how this works. So we'll start with 5x equals 20. Now I'm going to apply ln to both sides. Remember, ln, the natural logarithm, is a function. So what that means is that if 5 to the x is supposed to be equal to 20, then the logarithm applied to 5x is supposed to give the same result as the logarithm applied to 20. And again, this is not multiplication. Let me put this in bright red. This is not multiplication by ln. ln is a function, and we are applying the function to both sides. We're using 5x as input to the logarithm function, and we're using 20 as the input to the logarithm function. And because we have this equation, the result of applying ln to 20 and the result of applying ln to 5 to the x should be the same. Here's the property that I want to use. ln of a base v to a power m comes apart into m times ln of v. Okay, so I'm going to match this up on the left-hand side. And take apart. Okay, so m in this case is x, then times, oops, I apologize, I forgot the parentheses around the ln like that. So then ln, and then v is 5. Now there are some things you could do to ln of 20, but they're optional and I'm not going to bother with them now. Okay, so this is where we are. At this point, I do feel that I should show you the structure of both sides of this because, let me try this time, because I've found that students are sometimes confused about what this ln actually is. Again, ln is a function. Tell you what, I think I like the orange better, and let me make this a little thinner, a little darker. ln is a function, and we are applying it. We are not going to divide by the function ln. Instead, we are going to divide by this unit. We're going to divide by the number ln of 5. Okay? So let me show you that. Oop. Let me switch back to the regular pen here. Going to divide both sides by the number ln of 5. I can cancel multiplication by ln of 5 with that division, and that leaves us here. X equals ln of 20 divided by ln of 5. Now, a couple of things that I want to point out, because again, these are mistakes that I see. We have not divided by ln. Instead, we have divided by the number ln of 5. So ln by itself is just a function. ln of 5 is a function applied to a number. That's a number. In fact, if you want, you can ask your calculator what this number is. ln of 5 is about 1.61. Another thing that I want to make clear is that since we've divided both sides by ln of 5, we need to be sure that on the right we have the right-hand side ln of 20 divided by ln of 5. We are not dividing by 5, so it's not ln of 20 divided by just 5. There's an ln there. We are also not dividing inside ln of 20. So sometimes I will see students in this situation make a mistake like this and try to stick the division by 5 up inside the logarithm. That's not what you want to do. Instead, you have to respect the structure of these algebraic formulas. Now let me see what. Sorry, this highlighter feature is not doing exactly what I intended, but there you go. ln of 20 is a substructure. ln of 5 is a substructure. Both of those actually represent specific numbers, and this is the division that you need to do to solve this equation and isolate the x. Okay, well, having done that, let's go to the calculator and give this a try. Okay, so there you go. There's ln of 5. ln of 20, by the way, is 2.995. No, what is that? Is that right? ln of 20. Yeah, okay. Sorry, there was an extra parenthesis. So the number that we are trying to calculate is, and I'll use the two-dimensional layout here, ln of 20 divided by ln of 5. And there's the answer. It's approximately 1.86. Okay, so let me write this down on my notes over here. X is approximately 1.86. Now, if you wanted to check this, here's what you could do. Okay, so to check this answer, I'm going to hit the store button. That gives me the answer symbol. That means to use the answer of the calculation we just did. That'll be that number. Then the arrow here means to store it in memory, and I'll hit that button to get the x, so it's right there. Now I hit enter, that number is now stored in the calculator's memory. Now, remember where we were going with this. We were trying to solve 5 to the x equals 20. So if I calculate 5 to the x, the calculator will pull this number from memory x and do 5 to that number. So, with any luck, drum roll, we should get what? We should get 20. Okay, and so that checks that we've got the right answer. Also, remember we were we were expecting to find a number a little bit less than 2, and 1.86 is the right size approximately. Okay, so that is the solution to 5 to the x equals 20. Okay, let's go on to the next one. So the next equation is tricky for a couple of reasons. One is that the x, as you can see, is inside applications of the logarithm. The second is that there are x's in two different places. So on the left side, we have ln of x plus ln of 2x equals 9. So it's going to take a couple of steps to solve this equation. Okay, take a moment, try to solve this, and then I'll show you my solution. Okay, so here's the equation again. ln of x plus ln of 2x equals 9. There are several ways to solve this. Let me begin by suggesting that we try to bring all the x's together. That means that we maybe should try a put together manipulation. Okay, so I've got ln of x plus ln of 2x equals 9. Looking at this left-hand side where the two x's are, do any of the algebraic properties of the logarithm look promising? We need one that has addition of logarithm of something and logarithm of something else. That means we need to use that property. So what I'm going to do is match the right-hand side, ln of u plus ln of v. So you can see everything lines up. And that is equal to ln of u times v. Okay. So when I fill in over here, I need ln of u, which is x, that's right there, times v, which is 2x, and that's the replacement for the left-hand side. And then I'll just keep the 9 from before. So there you go. We've used that. Let me move my reference thing down a little bit. Now, at this point, I can clean up x times 2x. X times 2x simplifies into 2x squared. And I'll leave the equals 9. So now we've made some progress because we've got all of the x's together. There's only one place where there's an x. Now at this point, we have to figure out how to somehow get rid of this ln. So to do that, I'm going to write over here a couple of other things to remind you of. First is that if you have ln and you apply it to e to the u, the ln undoes the natural exponential and gives you just the u. This is actually a special case of this. The reverse of that is that e to ln of u is equal to u. E to a power undoes the natural logarithm. Again, the natural exponential function e to a power and the natural logarithm function ln, they are inverse functions of each other. So what that means is that I can get rid of the ln by applying the natural exponential to both sides. So that means I'm going to do e to the left equals e to the right. And I'm going to put ln of 2x squared here and 9 over here. So again, I'm applying the natural exponential function to two things that are supposed to be equal. And when you apply the same function to equal numbers, you get another equation. The whole point of doing that, as I said, is that now the e to the power undoes the ln and leaves us with just 2x squared. Okay, now this is starting to look a little more promising. We can divide by 2, which leaves us with x squared equals e to the 9th over 2. And before I do the next step, let me just clarify this. We are not dividing by 2 up in the exponent. Remember, the order of operations is still in effect. We are dividing the result of e to the 9th by 2. Let me also say this, that up here we did not multiply by e, not multiplication. We applied the function e to a power to the left, and we applied the same function to the right, and that's where this equation came from. Sorry, this equation, and then we simplified it to get this equation. Okay, which brings us back here to x squared equals e to the 9th over 2. How do you get rid of squaring? Well, you use the square root. So x equals square root of e to the 9th over 2. And here's where we get to some unfortunate complications. Remember that when you do the square root, that gives you the principal square root, the positive number that solves x squared equals this thing under the square root symbol. There are actually two possible solutions, one of which is the plus root, one of which is minus root. So you got to remember that. However, let me show you what happens. Let's check these two numbers in our calculator. So again, remember, this is the equation that we're trying to solve. So if I plug x into that equation, say the thing on the left-hand side, I ought to get a 9 out of it. So let's give this a try. The solution that we came up with was square root, and I'll put in a fraction, then second, and then this button to get e to a power, so it was e to the 9th divided by 2. And since I want to do a couple of different things with this, I'm going to store that into x. Okay, so there we go, 63.65. Let's check it. ln of x plus ln of 2x oops. Yeah, I have a straight parenthesis there, but the calculator lets you get away with that sometimes. So there's the result, 9. So that's good. But now, let's use a different letter here. How about A? Oops, I wanted to store the negative root. All right, let's try this again. So let me go over here, and I want to insert a negative sign in front of that square root. What? All right, let's try this again. Negative square root of fraction e to the 9th over 2 all the way outside the square root symbol. Store that into, into A. Okay, negative 63.65. Here we go. ln of A plus ln of 2A. And if all goes well, when I hit enter, I'm supposed to get 9. But instead, I get error non-real answer. Now, if you hit go to, it will show you exactly the calculation that it ran into trouble with, ln of A. So here's what's gone wrong. Remember that the domain of ln is just the positive real numbers. What the calculator means by non-real answer is that if you allow yourself to use complex numbers, there is a way to make sense of the logarithm of a negative number. We're not going to do that in this class. The calculator is set appropriately, so it's telling me that it's not going to compute that. It's not going to try to go into real numbers. Well, why is that causing a problem here? Well, if you go back to the original equation, there's an ln of x in it. So if I try to put in a negative number for x, this thing that I've circled in black is not a real number. That means that we should not consider that negative number as solving the equation. So here's the vocabulary you might see. So first of all, x equal to square root of e to the 9th over 2, which is approximately, what was it? 63.65 is a solution. But negative square root of e to the 9th over 2 is something called extraneous. What that means is that it actually solves this equation, it solves this equation, it even solves this equation. However, it does not solve this equation, because if you try to plug it in, the first thing you'll do is take the logarithm of a negative number, and that can't be done with real numbers. So an extraneous solution to an equation is, again, one of these things where you get down to the bottom and it solves several equations that you've been working with, but it does not actually solve the original equation. So you should always check for that and know that this or this is what you should type in on the homework. And there are some problems on the homework that I've seen where you get extraneous solutions. Let me also show you again that there are some numerical issues that you have to watch out for. If I type in ln, oops, if I type in ln of 63.65 plus ln of 2 times 63.65, the answer will be close to 9, but not exactly. So you can see there it's 8.9999 and a little bit. That's because if you notice, I've truncated it to 2 decimal digits I've rounded it to the nearest hundredth, 63.65. So that means that the 63.65 is very close to being a solution, but it's not exactly. That's just something that you should keep in mind while you're checking these. There are other ways to solve this problem. I'm going to very quickly show you another solution. Okay, another solution method. Here's the equation again. ln of x plus ln of 2x equals 9. This time, instead of starting with putting together, I'm going to start by taking apart. Okay, ln of 2 times x comes apart into what? Ln of 2, oops, I misread. All right, ln of 2x comes apart into ln of 2 plus ln of x. Now, if you notice, I have like terms. So ln of x plus some other stuff plus another ln of x, I can combine that into 2 times ln of x. Okay. Now I need to undo the addition of ln of 2. So I will subtract ln of 2 from both sides. That leaves us with 2 times ln of x on the left. That's equal to 9 minus ln of 2 on the right. Next step is to undo multiplication by 2. So to do that, I'll divide by 2. Be careful that you divide the entire left-hand side by that 2. That leaves us with ln of x equals 9 minus ln of 2, all divided by 2. Now I need to get rid of the ln layer, so I will apply the natural exponential function. So e to the left, ln of x, should be equal to e to the right, 9 minus ln of 2 divided by 2. And the point of doing that is that, as you should recall, e to the ln of a number simplifies to just that number. So I go down here, e to the ln of x simplifies into plain old x. It just so happens that doing things this way, we've done something that doesn't involve a square root. What happened was we divided by 2 instead of taking a square root. See if you can figure out what I mean by that. That means that we ended up not discovering that extraneous solution that solved some other equations but didn't actually solve the original equation. It's just something that happens. Sometimes one solution method generates extraneous solutions and another one doesn't. Every equation is a little different. One thing that you should calculate, just to see, is that if you do actually type that into the calculator, let me switch back to the calculator. If you do actually type this in, so second and then this to get E, alphabet and this button to get the menu, and then N over D to get the fraction template, 9 minus ln of 2, close up the ln, and divide by 2, and I think we're good to go. There's the 63.65 again. So sometimes when you do a different solution method, you get a different formula for the same number. If you really wanted to, you could use properties of logarithms and exponential functions to convert one of these forms into the other. It's just something you should know about our algebraic toolkit. Okay, here's another one. 6 times e to the negative 0.4t equals 45.5. Okay, so take a minute and try to solve that one. Okay, let's try to solve this. One thing that you should immediately see is that there's e to a power, and the t that we're trying to solve for is up in the exponent. That means that at some point we're going to need to use the logarithm. However, if you look carefully at this, you'll see there's multiplication by 6, so it may be a good idea to handle that first, and we'll save the logarithm for a future step. So let me write this again. And to undo multiplication by 6, we need to divide by 6. So I'm going to divide both sides by 6. That will leave me with e to the negative 0.4t on the left equals 45.5 divided by 6 on the right. I'm going to leave this unevaluated and do all of the calculations together in a moment. Well, now the outermost operation on the left is indeed that exponential, e to a power. Now would be a good time to apply ln to both sides. Okay, so let's figure this out. I need ln of the left equals ln of the right. So ln of e to the negative 0.4t equals ln of 45.5 divided by 6. Again, the point of doing that is that ln of e to a power, well, ln and e to a power are inverse functions. We're going to be left with just the negative 0.4t that was up in that exponent. The left-hand side I'm going to just leave as ln of 45.5 divided by 6. Again, be careful. Sometimes students forget to put the ln around the right-hand side when doing something like this. Be very, very careful. Now this is looking more promising because on the left I just have multiplication of t and a specific number, negative 0.4. So I can divide both sides by negative 0.4t, no, sorry, by negative 0.4 to isolate the t. Now, just think for a minute. Where exactly does the division by negative 0.4 go over here? Yep, it has to go like this. The entire ln of 45.5 over 6 has to be divided by negative 0.4. In particular, we are not dividing somehow up inside the logarithm. The result of the logarithm has to be divided by negative 0.4. Okay, so that leaves us with t equals ln of 45.5 over 6, whole thing divided by negative 0.4. let's go to the calculator and figure out what this number actually is. Okay, I need to set up division, so I'll do this, then ln of, and I need to, well, I can set up another fraction like this, 45.5 divided by 6, and all of that is divided by negative 0.4. And I'm going to save that. I'll hit the store button, and you could save it in any letter that you want, but since we're using T, I'll use T. So where is the T? The T is here on the 4 key. So we do that, and we get T equals negative 5.06. To check this, let's go back to the original equation. If I do 6 times e to the negative 0.4 t and fill in my value for t, I should get 45.5. Let's see if we can make that work. Okay, 6 times e to the power negative 0.4, and then alpha, and where's the t again? T. So, fingers crossed, this should result in 45.5. There we go, 45.5. So far so good. Just because I know some students have calculators that only do left to right notation, I'm going to convert this calculator back to classic mode, as it's called, and type in this result again. So let me first of all show you my notes, my written work here. I need to divide the result of ln of 45.5 over 6, and you divide that whole thing by negative 0.4. Okay, here goes. Since the top has ln as its outermost operation, and function application happens earlier than the division bar, I don't absolutely have to have parentheses around the top. It wouldn't hurt to have them, but I don't need them, so I'm going to leave them out. There's the ln of 45.5 divided by 6, and then divide, and since the number underneath, well, I will put parentheses here just to be safe. Okay, so if all goes well, I should get the same number as I got before, and sure enough, there it is. If you have any doubts about this, you can always do the calculation one piece at a time.